Problems from both chapters 2 and 3. Also, the very last thing I did on the board last time, I had wrong. And I sent you an email about that, but just so that it's in the official recorded register here, I wrote that specific volume equals molar mass times molar specific volume, but it's actually the molar specific volume divided by the molar mass is a specific volume. What you'll find is that in some equations or some tabulations of data, it will give you the specific volume, and in others, it'll give you the molar specific volume. It's really easy to switch from one to the other. You just take your molar specific volume and divide by the molar mass, and then you have the actual specific volume. Usually it's the actual specific volume, which is our inverse of density, right, that we're going to use in problem solving. So just fix your notes from last time. That's all I really wanted you to do. Question?
This homework is due next week?
Yeah, so this is week 2's homework for the entire week, and it'll be due a week from Wednesday. Those 8 problems from chapter 1 from last week are the only ones that are going to be due this coming Wednesday. And I think, as I mentioned before, they don't have to be in any particular type of paper, just any clean paper written on one side I would prefer. So I'll just have you make a pile as you come to class, and I'll post the solutions outside my office Wednesday when I get back to my class. So let's just continue from last time. We're talking now about some different properties. We've talked about volume and specific volume now. The next one that I want to talk about is pressure. So we're really just continuing from before. All right, so when we talk about pressure, hopefully we all understand that pressure is really just the force per unit of area. And we're not going to actually be measuring force and area. We actually have a pressure gauge that we can hook up to any old system. So the pressure is what we're actually going to measure. So pressure is one of these intensive properties that's really quite measurable, and therefore it's going to be used all the time. We're interested in the units of pressure. The force units are, of course, newtons. The area units are meters squared. So a Newton per square meter is the appropriate pressure unit in the SI system. And we should all understand that this is what we define as a Pascal. So 1 Pascal is just 1 Newton per square meter. I might note that often, because a Pascal is a very, very, very small amount of pressure, usually we would measure, at least in the SI system, using kilopascals or thousands of pascals, right? So 1 kilopascal is going to equal 1,000 pascals. We also may have some problems where we're going to be in the megapascal range. So, 1 megapascal is just 1,000,000 pascals, or if you will, 1,000 kilopascals. So just be aware of this. These are common units. The kilopascal, much more common than just Pascal. Now that's in the SI system of units. We also want to look at the British system of units, of course. And in the British system, our force units are not the Newton, they're the pounds force. And our length units are going to be feet. So pounds force per square foot is one of the common units that we would use. Now, most of you have never heard of a pounds per square foot, which we might just abbreviate PSF. Unless you're a civil engineering major, and thankfully you're not. So, well, that's okay. There's nothing wrong with civils. It's just you're not them. And we usually use a pound per square inch. So if you take a pound per square foot and you just divide by 144, then that's going to give you in pounds per square inch. So the most common unit in the British system, anyway, is actually the pounds per square inch, which we just abbreviate as a PSI. So, yeah. So these are the common British units. That'd be the PSI, and the common SI units is typically just going to be the kilopascal. So those are the units that we're going to deal with primarily. Now, we do have to be aware of one other thing with regards to pressure units. The actual pressure is what we call the absolute pressure, or we can call it the actual pressure. But it's very common in industry and out there in the real world to take a pressure gauge and stick it onto our system, maybe it's a tank or a pipe or whatever, and then adjust that gauge to 0 so that the pressure on the pressure gauge would read 0. But that's clearly not the pressure. This is just a tool that's used. What you'd want to do, if you've zeroed your pressure gauge, then you're going to have to add the atmospheric pressure back on to whatever that gauge pressure says, and that's going to give you the actual pressure. So more often than not, you're just going to have your pressure in the actual scale, your absolute scale, but with the understanding that sometimes we have to add the gauge pressure onto the atmospheric pressure to get this actual pressure. So I'll just write it this way. P actual is going to be the pressure on the pressure gauge plus the pressure in the atmosphere. And this actual pressure is sometimes called the absolute pressure. Okay. Now, if we were in, let's say, the British units, so we'll just do British units, we're going to have the pressure, and again, I'm going to use square brackets to represent the units here. So the pressure in PSIA, that is A standing for actual, really it stands for absolute, but think of that as the actual pressure. The actual pressure is going to be the pressure measured in PSIG, and this G implies the pressure gauge. But again, we've set that pressure gauge to 0, so the actual pressure is really whatever the atmospheric pressure is plus whatever registers on that gauge. If you add some pressure to, let's say, the gas that's in that tank, and it goes from 0 up to 1 up to 2, that doesn't mean that 2 is the actual pressure. It means that 2 is the pressure above the atmospheric pressure, right? Because at atmospheric pressure, the gauge was set to 0. So we have to add to this pressure in the pressure gauge the pressure of the atmosphere. Okay. So we need to make sure that we do this properly. In essentially all problems, we need to use the absolute pressure, but often, not always, often it's the gauge pressure that would be given. So all I'm really saying here is be careful. Make sure you know what pressure it is you're dealing with. Now, in the SI system of units, the general equation up here still applies, but we don't use PSIA or PSIG. You know, we don't even use, well, the pressure would be in Pascal, so we don't have Pascals with a subscript A or a subscript G. It's just understood based on the way the problem is worded. So anyway, be real careful. In the British system, though, we definitely have a subscript G and a subscript A to make that distinction. Let me also just note, just so you're aware, that standard atmospheric pressure is, that is the pressure in the atmosphere, is either 14.696 pounds per square inch, or if we're dealing with the SI system, it's 101.32 kilopascals. So this is standard atmospheric pressure. In other words, atmospheric pressure at standard sea level would be measured like this. Now, if you were given the gauge pressure, if the problem doesn't say anything, then just assume that the standard atmospheric pressure is the atmospheric pressure, but sometimes it's not. Sometimes you'd be like, say, up at Big Bear, up in the mountains somewhere, where the atmospheric pressure is less than the 14.7. Or sometimes you'd be like, say, at Death Valley or the Dead Sea or somewhere well below standard pressure, well below standard sea level, in which case your pressure might be closer to 15 point something PSI, or certainly something higher than the 14.7. So again, be real careful when you're dealing with pressure. Just make sure you have the units done correctly. So any questions just in general?
101.32 kilopascals?
Yes. That's 1 atmosphere is equal to that number of PSI or that number of kilopascals. Okay. All right, so again, so much for temperature. By the way, I'm sorry, so much for pressure. By the way, the author does talk about different pressure measuring devices, barometers and the like. And I think it's in section, 9, 10, something like that of chapter 1. We're not going to be concerned with that in this class. We're just going to accept that whatever the pressure is that's given to us was probably calculated or measured properly on whatever gauge. We're not going to have to worry about pressure gauges. Eventually we'll be taking an engineering measurements class, and you'll learn all about various types of pressure gauges and other types of gauges. So in this class, don't really worry so much about those sections that deal with pressure measuring devices. We're just going to use pressure as if it were any other property that we're interested in this class, which then moves us on to temperature. Okay. So temperature is one of those interesting ones. Most of you are probably very comfortable with the idea of temperature, but maybe you aren't, even though you think you are. So let's say that we have a room, I don't know, how about this room, and let's say it's 70 degrees Fahrenheit. And let's say that it's a cold day like today, and we come into this room, and this room actually feels rather warm to us, right? But it's at 70 degrees. On the other hand, let's say that we're in the, I don't know, summer semester, and let's say that it's 105 degrees outside, and we walk into the same 70-degree room, and now this room feels cold, okay? So you're in the same room at the same temperature, yet one day it feels hot, one day it feels cold. The whole point behind this discussion is that you shouldn't confuse heat with temperature. Heat is a measure of how much energy is transferred between two objects that have different temperatures. If your skin is cold because you've come inside from a cold day, then of course the room feels hot, right? Heat is being transferred from the warmer room to your colder skin. On the other hand, if you are in, if you're outside and it's the summertime, your skin is actually quite hot, you come into this room and now heat is being transferred from your warmer skin to the cooler room, and that transfer of heat away from you is what you feel as cold. So you shouldn't confuse the ideas of heat or heat transfer, cold and hot, with the idea of temperature. Okay, temperature is a thermodynamic property, and it's actually a measure of the vibration of the atoms that make up that substance. Okay, it has nothing to do with heat transfer. So please be aware of that. Temperature does not equal heat transfer. It's two completely different ideas. All right, so just be aware of that. And again, it should be understood that temperature, and T is the variable given to temperature, is really a measure of the vibrational energy of a substance. By the way, today I'm just using a standard pen. Last time I used one of these kind of fat Sharpies. I assume you guys can read what I'm writing okay? No loss of clarity because of the thinner pen? All right, so I think I'm just going to use a regular pen because it just works better for me. It doesn't help my writing. It's still kind of sloppy, but I'll do the best I can. Anyway, so don't confuse temperature with heat. Now, the first thing you're going to read about when you begin to look at, well, this section that deals with temperature is something called the zeroth law of thermodynamics. Okay, I am not really that concerned about the zeroth law. The zeroth law basically tells us that a device called the thermometer works. What it really says is that two bodies that are in thermal equilibrium with two bodies that are in thermal equilibrium with a third body are in equilibrium with each other. You can think of that third body as the thermometer, right? If the thermometer, putting it in one cup of water, says that it's at 70 Fahrenheit, and then you put that same thermometer in another cup that's also at 70 degrees Fahrenheit, well, then there's no temperature difference between the two, and they're in thermal equilibrium. That's really what the zeroth law tells us. But that's not something that really helps us solve thermodynamics problem. So what it really does is just tell us that we have a way of measuring temperature. So I'm not that concerned with the zeroth law. I guess I should write it down just so we know that two bodies, each in thermal equilibrium with a third body, are in equilibrium with each other But again, in my mind, all it really tells me is that we have, the existence of a thermometer, which is that third body. So, in other words, thermometers allow us to find temperature. Now, there's a lot of different types of thermometers, and many of these aren't even called thermometers. Some names like thermistors and others, but they're all basically the same type of device. However, what is important as we talk about temperature is the temperature scale that's going to be of use to us. So let's look at some temperature scales here. So first of all, you know two of those temperature scales, right? You know the Celsius scale, which used to be called centigrade, and the Fahrenheit scale, all right? You all know those, you are comfortable with those, and they're both completely arbitrary and totally useless from a thermodynamics point of view, okay? So like them as you may, why is a temperature scale simply based upon where water boils and freezes valid? Well, it really isn't, right? We should have a temperature scale that is based upon absolute zero. If you go into the complete vacuum of outer space where there is no matter and there's nothing to transfer heat to or from, I mean, that's as cold as you can get. That's absolute zero. We should actually be using temperature scales based upon the existence of absolute zero, not where water happens to boil or freeze. So we will note that the Fahrenheit and the Celsius scales are arbitrary. Okay, maybe I could do it this way. Here's a thermometer, and this is where water happens to freeze, and this is where water happens to boil. And if we wanted to look at where this happens in the Fahrenheit and the Celsius scales, in the Fahrenheit scale, it happens to boil at 212 degrees, at least at standard atmospheric pressure, right? And it happens to freeze at 32 degrees. In the Celsius scale, it happens to boil at 100 and happens to freeze at 0. But again, those are arbitrary based upon what's happening to water. We need a better scale. So we need a scale where we come all the way down to absolute 0. And that's what we want to base our temperature scale on, okay? So I suppose the question is, well, how do we do that? So what's been done is various conferences were held. They're still held every several years or so. And somebody decided once upon a time to say, well, let's just let 1 degree of Fahrenheit still remain. I'm not saying 1 degree, I'm saying 1 degree of, the individual graduations that we just call 1 degree in the Fahrenheit scale. Why don't we come up with a new temperature scale where it has a numerical value of 0 at absolute 0, but each unit of that scale is the same as a Fahrenheit scale. And then somebody else said, okay, but let's do the same thing for Celsius. I mean, you might notice that a degree of Celsius is 80% bigger than a degree of Fahrenheit, right? I mean, you all know that 1.8 number from some old class, probably in junior high school. 1 degree of Fahrenheit, we would actually multiply, 1 degree of Celsius, if we multiply by 1.8, that's the number of degrees in Fahrenheit. So anyway, somebody else came up with the idea, well, let's do the same thing for Celsius. Let's let 0 absolute exist in this new scale, but let's let each individual graduation on the thermometer, each degree, be the same as a Celsius scale. And what was come up with then were two competing scales. One is called the Rankine scale, and the other is called the Kelvin scale. So we will use the Rankine scale whenever we're dealing with where we would otherwise use the Fahrenheit scale. In other words, in the British system, we're going to use Rankine, and in the SI system, we're going to use Kelvin. Okay? So in the British system, temperature, if we measure it in Rankine, and I'm just going to use R for Rankine, that's going to equal the temperature in degrees Fahrenheit, but we actually have to add 459.67 in order to convert from Fahrenheit into Rankine. Remember, we're starting way down here absolute zero, it turns out that at the point where water is actually going to freeze, we have to add 459. So what's that? This is 491.67. And then we have to add another 180 degrees onto that. So let's see, 212 plus 459.67 is what? 471? I'm sorry, 671.67. So this right here is the Rankine scale. It starts at absolute zero, and when it gets to 491, that's when water is actually going to turn from freezing water into liquid water. And then when it gets to 671, you're going to finally get to the point where water boils. But this is one of the absolute temperature scales that we're going to use. We'll use the Rankine scale. In the SI system of units, it's a little bit different. The temperature in Kelvin is going to equal the temperature as measured in Celsius, but plus 273.15. So over here, when we look at where water freezes, we're actually going to have to add 273. So at 273.15, that is where water is going to freeze, or at least change from a solid to a liquid. And then at 373.15, that's where water is going to boil from water into steam. So that's the Kelvin scale. Okay. So these are the two scales that we're going to use. I would go so far as to say that whenever you have a problem where you actually have to use temperature within that problem, then you're definitely going to be using the Rankine scale or the Kelvin scale. Okay? Now, that doesn't mean we're always going to use those scales. One thing you may have noticed if you go into the last 100 pages of your book, when you have all those appendices of thermodynamic property data, more often than not, the data will be tabulated using the traditional scales, Fahrenheit and Celsius. But if you're going to have to use one of those temperatures in problem solving, like within an equation, then you're always going to want to convert it from, again, Celsius or Fahrenheit into the appropriate absolute temperature scales. Okay. So just be aware of that. Rankine and Kelvin are called absolute temperature scales. Okay, and those are the ones that we're going to use. I might also note that if we're looking at, let's say, a temperature difference, 1 unit of a degree, delta T of 1 degree of Celsius equals 1 degree of Kelvin. Okay, and delta T of 1 degree of Fahrenheit equals 1 degree of Rankine. Okay, but note that this says delta T. We're talking about the length between one graduation and the next on our scale, right? I'm not saying that 1 degree Fahrenheit equals 1 degree Rankine. I mean, clearly that's not true, right? 1 degree Rankine is way down here. 1 degree Fahrenheit is way up here somewhere, right? Same with Celsius. 1 degree of Kelvin is way down here near absolute zero, and 1 degree of Celsius is way up here near the freezing point. So I'm not comparing actual temperatures here. I'm simply saying that a unit of degree, that temperature difference from one temperature to the next, a degree of Celsius is the same as a degree of Kelvin. A degree of Fahrenheit is the same as a degree of Rankine. And I might also note that you're never going to switch unit scales within any problem. If you're given a problem in the SI units, solve it in the SI units. If you're given a problem in the British units, solve it in the British units. You're never going to want to swap from one to another. I often will have some students that just become more comfortable with the SI scale because you don't have all the conversion factors like you do in the British scale. So they'll take every British problem, convert it into the SI units, and then solve it in those units. But you don't want to be doing that, okay? Whatever the problem is at hand, use the appropriate scales for that problem, or the appropriate unit, I should say, for those problems. That doesn't just apply to temperature, it applies to everything. So are there any questions then, just in general, about temperature? You'll read more in the book. You'll see how to physically convert from, let's say, Kelvin into Rankine if you need to. I've given you the equation already to convert from Fahrenheit to Rankine, Celsius into Kelvin. So you do have some problems where you're going to have to deal with that. Anyway, so much for temperature. Any questions on temperature? Remember, temperature is an intensive property. It's also a measurable property. So like pressure, these are going to be the two properties that we're going to use for practically every single problem. Remember, if we have two independent intensive properties, that sets the state for us. We can go and find any other property knowing any two independent intensive properties. So most of the time, temperature and pressure are going to be two of the intensive properties that we're going to have available to us. We'll use those to find other properties, and we'll be talking more about that either by the end of the week or next week. Yes?
So for Kelvin or Rankine, in the Rankine temperature, we don't have a degree symbol, but when we're talking about individual units, we do have a degree symbol?
You know what? It's really arbitrary. Sometimes I forget the degrees, and sometimes I don't. Some books don't even use a degree symbol. Some do. I've done it both ways here, right? And I probably shouldn't. I should be more consistent. So usually I wouldn't even use a degree symbol for Kelvin or Rankine. I would just say Kelvin is the temperature degrees, Rankine is the temperature degrees. But you're all used to using a little circle symbol for degrees Celsius or Fahrenheit. So yeah, I would say don't worry about the little circle for degrees. Just a K or an R would be fine. Any other questions on temperature? Okay. I will note lastly that the final section in chapter 1-11 deals with problem-solving techniques, and it's just way too early to talk about it now in this class, so I've got it in your syllabus for like the beginning of the 4th week. We will talk about that section, but not quite yet. All right, so continuing with this discussion of different units, let's talk now about energy. All right. Now, we've talked a little bit about energy. I think we understand just intuitively what energy is. Energy is really just a measure of the ability to do work or the ability to transfer heat. If we look at energy, the variable that we use, E, is what we just call the total energy. And this is actually the sum of the energy contained internal to our substance plus the energy due to outside forces or motion. So this is equal to the energy contained internal to our substance. And in fact, the letter we give is U. So this is not a V, this is a U. It has a nice rounded bottom here. So the total energy is the energy, oops, I put a T there. This is the energy contained internal to our substance, U, plus the energy due to outside forces or motion. Okay. So what would be those other types of energy? What would be the energy due to outside forces or motion? Now, there's certain things we're specifically neglecting, right? We're dealing with our simple compressible systems. We're not dealing with magnetic forces. We're not dealing with electrical forces. We're not dealing with any kind of chemical reactions taking place. But there are still some other forces that are going to be so common that we do want to include them in our general equations. First, with regards to outside forces, how about the gravitational force of the Earth? So one of those forces that we're going to deal with is basically gravity, and this leads us to what we call potential energy. Okay. So in this class, the potential energy is just going to be PE for potential energy. Now, if this were your dynamics class, some of you have had dynamics already, they would make a distinction between gravitational potential energy and elastic potential energy due to a spring. We're not going to worry about that. I'm just going to say there's only one potential energy that we're going to utilize in this class, and that's just the gravitational potential energy. It's a potential energy based on the substance's position in the gravitational field. So this is just going to be mg times the height z. So that's just mgz. I like to put a line in the middle of my z just so there's a distinction between that and the number 2. So that's the potential energy. It could be called gravitational potential energy. If this were your dynamics class, this would be Vg, right? Why V for potential energy? I have no idea. We're just going to use PE. It makes more sense. Okay. What about motion? What might be something based on motion? Well, all objects at least have the potential, all substances have the potential to be moving. So this is really our, what we call kinetic energy. So the kinetic energy, or the energy based on motion, I'll just call KE for kinetic energy. If this were your dynamics class, it would be T. I mean, who uses T for kinetic energy? But, well, the Merriman-Craig book does. So I'm not going to call it T. KE, kinetic energy, makes a lot more sense. And this is just 1/2 m times the velocity squared. Please note that lowercase m is mass, right? And the lowercase v, in this context, I use a cursive letter v, and that's velocity. Okay, the specific volume was also a lowercase letter v, but it had a little pointy bottom and it looked more like the Greek letter nu. So this is how I'm going to make my distinction between specific volume and velocity. So this lowercase cursive v is the velocity. Okay. By the way, if it wasn't obvious, above g is the acceleration of gravity, and I think I already wrote that down somewhere once upon a time. So with all this in mind then, if the energy is really just the sum of the energy contained internal to the system plus the energy based on motion and other forces, well, then that means, therefore, that E is just equal to U plus the kinetic energy plus the potential energy. So we could just write it as U plus 1/2 mv squared plus mgz. Okay, so this is our equation for energy. Now, the units we also have to be aware of. Energy units are the same as work units, or the same as heat units. We had previously talked about the joule, which is the same as a Newton times a meter. Turns out a joule is also a very, very small amount of energy. So the kilojoule, 1,000 joules, is the most common unit of energy, at least in the SI system. So the kilojoule is the proper unit here. Or if we're dealing with the if we're dealing with the British system of units, then the British system of units, the typical unit of energy is going to be the BTU. Okay. Now, most of you have probably heard of a BTU before. A BTU stands for British Thermal Unit. Again, we're the only place in the world that uses BTUs, but still, those are the appropriate units. Originally, a BTU, I believe, was the amount of energy that it took to raise a pound of water by 1 degree Fahrenheit. I think that's what a BTU was. But nonetheless, the BTU is the standard energy unit in the British system of units. British Thermal Unit, or the BTU. Now, I might also note that since energy is the same units of heat, the same units as work, work units are force times distance units. I think we saw this last time. Now, force times distance would be like newtons times meters or kilonewtons times meters. So that's the same as a kilojoule, right? I mean, 1 kilojoule is just 1 kilonewton times a meter. But we also have equivalent units in the British system. If we multiply force times distance, then we have pounds force times feet. We can call this pounds foot, we call it a foot pound. Now you may say, well, is that equal to a BTU? No, it doesn't equal a BTU. So in the SI system, everything is easy. 1 kilojoule equals 1 kilonewton meter. In the British system of units, it's not quite as obvious. 1 pound force times foot does not equal a BTU. So you are going to have to use conversion factors. If you go to the inside back cover of your textbook, although if you have an electronic textbook, I guess it would be somewhere near the end in there somewhere. But there's a whole set of conversion factors in there for you for every conceivable unit. So if you happen to have your textbook, let's say you have units, you need to switch from BTUs into foot pounds, then just look up the appropriate conversion factor. I'm sure you'll find it right away. So again, use conversion factors in the British units. Okay, and again, just look them up in the inside back cover. Anyway, back to the equation up here above. One thing that we can do if we choose to is we can divide by the mass. So if we divide by the mass m, we get E over m equals U over m plus v squared over 2 plus gz. Now, remember last time we talked about how you can divide by mass and get what we call the specific property? So capital letter E is the total energy. E over m would now be what we call the specific energy, and it would be listed by using its lowercase rather than its uppercase. So E over m is the same thing as lowercase letter e. We'll just call this the specific energy, or if you will, energy per unit mass. It means the same thing. U over m is lowercase letter u. So if capital U is the total internal energy, then lowercase u would be what we'll just call the specific internal energy. And then we just add to it v squared over 2 plus gz. So this would be just another form of the equation. You know, the top form says that the total energy is the total internal energy plus the total kinetic and potential energy. The specific energy is equal to the specific internal energy plus, well, this would really be the kinetic energy. We might want to call it kinetic energy per unit mass, and this would be the potential energy per unit mass. Typically, though, I'll just call it kinetic energy and potential energy. So anyway, plus Ke plus Pe. If we look at the units associated with this problem, the units are going to be the same as above, but divided by mass, right? So it's either going to be kilojoules per kilogram would be the typical units for specific energy or specific internal energy, or if we have the British system, then it would be typically BTUs per pound mass. Sometimes foot-pounds force per pound mass, but more often than not, BTUs per pound mass. And in fact, when we look at our property tables, we'll see that the BTU is the more common energy unit when we're dealing with the British system. Okay, so let us just continue. Remember, this is all still basics. We're still just learning about basic concepts and terminology and definitions and all that. Two more properties that I want to at least introduce you to. Okay, so the first one is enthalpy. And the enthalpy is given just a capital letter H. And by definition, enthalpy is actually a combination of other thermodynamic properties. It's just the internal energy plus pressure times volume. So U is a property, P is a property, V is a property. It turns out you can combine properties in any mathematical way, whether it's this way, which is just algebraic, or we can also combine properties using, well, differential equations, partial differential equations. We'll look at all sorts of possibilities. But we should at least be aware that enthalpy is one of those properties that is commonly used. We don't really know why we're going to use it. We don't know how we're going to use it. But just be aware that it is a property, and we will use it. Another property of interest is called entropy. And entropy, we just use the capital letter S. I'm not even going to bother to define entropy for you right now. When we get to Chapter 7, we'll talk all about entropy. But again, these are real properties. They're observed characteristics of our substance, but they're not measurable. We're going to need enthalpy and entropy to solve certain types of problems, but we can't measure it. But that's actually okay, isn't it? Because as long as we can find two other independent intensive properties, like say pressure and temperature or specific volume, as long as we have any two properties like that, all other properties are known to us, right? That's why we have these property tables to begin with. We're going to need to find the unmeasurable properties like enthalpy and entropy to solve certain types of problems, but we're going to have to find those given the measurable properties like, again, pressure and temperature and some of the other intensive properties. So right now I'm just introducing you to certain properties, and these are the latest two. I might note that we can also divide these by mass. So for instance, if we divide the enthalpy by the mass, Well, now we get lowercase letter h, just like for everything else. The total volume over its mass was lowercase letter v. We call it specific volume instead of volume. The total internal energy divided by mass is a specific internal energy. The total enthalpy divided by mass is now called the specific enthalpy. So this is the specific enthalpy. And remember, specific properties are intensive properties. So we're going to actually find a relationship between those measurable intensive properties like temperature, pressure, specific volume, and the non-measurable ones like specific enthalpy. Same thing with entropy. The total entropy divided by the mass is going to be lowercase s, and we call that specific entropy. Okay. Now, one thing that I also want to mention at this point is that, in fact, let me add internal energy to this. We've already seen that on the previous page. Well, the reason I bring this up here is because when you're reading through the textbook, the author will often be discussing specific enthalpy or specific entropy or specific internal energy, but only use the word enthalpy or entropy or internal energy. It will be implied that the author is talking about specific values, even though the author never writes the word specific into the book. So I just want you to be aware of that. Look at the problems, look at the context of the problems, and just be aware that the author, more often than not, just doesn't use the word specific within the textbook, even though he means to. Anyway, this one is specific internal energy. And again, as a note, the author often means specific even though he doesn't write the word specific. So, again, just for you to be aware of it. It's not a big deal, but still something to be thinking about. Yes?
At the top where it says U plus PV, is that a capital V for volume?
Yes, yes. It is. And in fact, one thing that I would also write, I probably should have written it here, so maybe I just will. If I divide by mass like I've done below, look what happens if we divide the enthalpy by the mass. Here's another thing for Michaela, my technician in the back there. When I'm finished with one page, is it possible to freeze that one page and move it over to the second screen, and then I don't have to kind of keep doing this half page moving at a time thing?
Not by my understanding, but I can ask for you about solutions.
Okay, I mean you don't have the ability to, I don't know, push command control something and automatically do a screenshot and leave the screenshot on one board? No? Okay. Yeah, maybe there's a way to do that, because then, I'm just always finding that it's a little more difficult having only one panel of the board open to the students at any point in time. Anyway, yeah, so if you could look at that, I would appreciate it. All right, so anyway, if we have our enthalpy term and divide it by mass, then that's the same as U plus PV divided by mass, which is just U over the mass plus P times V over the mass. And therefore, H is just going to be lowercase letter u plus pressure times lowercase letter v, right? So this is just another alternative way of writing enthalpy. Enthalpy certainly is defined as capital U plus capital P, capital V. These are all capital letters. But we can also divide out the mass and then just write it in this fashion. Now, this is just how enthalpy is defined. You don't have to stress out over it. It's just a property. I'm never going to ask you to calculate enthalpy by pulling 3 separate pieces of data out of your tables and then adding them or multiplying together like you've done here. There's going to be enthalpy data in your tables. So you just need to be aware of where enthalpy comes from And I spend more time than perhaps I should, primarily just to make sure you understand that we can combine other properties like U, P, and V into new properties like enthalpy. All right, so now let's continue. And now let's talk about energy, specifically energy transfers. Okay. So when we talk about energy transfer, and I know I've alluded to this in the past, there's really only two ways that we can transfer energy. One is by heat, and the other is by work. Okay? If there's a temperature difference between my system and its surroundings, then it's heat that's going to be transferred. That's how the energy is going to go from one to the other. If, on the other hand, there's some imbalance in forces, if we're pushing onto our system from the surroundings, or if the system is pushing onto the surroundings, maybe it's a flexible container like a bag, and if we're able to expand or contract that bag, well, then work is being done. We're adding a force, we're changing the volume, we're moving a force through some distance, so that type of energy transfer would be considered work based on an imbalance in forces, as again we've talked about last time. What we need to do now is make sure that we understand a little more about the units, the sign convention. So we're talking about basics. Please keep in mind another thing I mentioned last time. We're not really concerned about the modes of heat transfer, or really the modes of work. There's lots of different ways that you can transfer heat. You may have heard the words conductive heat transfer, or convective heat transfer, or radiative heat transfer. Those are just different modes of heat transfer. You'll learn about that in your heat transfer class. In this class, we don't care. We just are concerned about how much heat is transferred, how that affects the substances that we're analyzing. For the most part, that also applies to work. There's a particular type of work that we call boundary work that we'll talk about in some detail, where we have a changing boundary. That's what we call boundary work. There's some other forms of work. We've got electrical work. We've got work based on a spring. We'll probably cover some of those a little bit, but not a whole lot. You'll read more about those in Chapter 2. Anyway, so we understand that energy can be transferred, right? It not only can be stored internal to the system, but can also be transferred. It has to be transferred at the boundary, so any problem we're looking at, we need to understand where the boundary is, and that's usually not a problem, right? The boundary is the interface between my system and its surrounding. It's the surface of the pump, it's the edge of the tank, it's the edge of the piston cylinder device. It's not going to be hard to determine our boundary. But nonetheless, as we look at heat first, and then we'll talk about work. The first thing we want to note is that it is a transfer at the boundary, right? It is not a property. Yes, so H, I should have written, well, that says it. It's supposed to say it. Heat. It is transferred at the boundary. It is not a property. Okay. Nothing has inherent heat in it, right? And this gets right back to that very first example I gave you about coming into a room at one temperature on a cold day or on a hot day, right? Heat is the transfer of energy that you feel. If you're colder than something, heat gets transferred into you. If you're hotter than something, heat gets transferred out of you. But that's the nature of heat. It's a transfer at the boundary. It is not a property. If we look at the units, then these are the same units as we saw before, right? Heat is a form of energy. It's an energy transfer. It's a form of energy, so it's got the same units. The units are either going to be kilojoules if we're dealing with the SI system, or typically BTUs if we're dealing with the British system. Okay, so those are the two units that we're going to be dealing with here. It should also be noted that, is that better? It should also be noted that if heat is transferred to the system, then it's considered positive. Okay, so heat is positive if added to the system. Okay, so this is our sign convention that we're always going to use. I might note that if heat is being removed from the system into the surroundings, then the heat is considered to be negative. So that should be pretty obvious by this statement. So heat is positive if it's added to the system, and then obviously then it's negative if heat is taken away or removed from the system. The letter we use for heat is Q. Okay, so Q would equal heat, and again it would have either the units of kilojoules or it would have the units of BTUs. Now, if the heat is transferred on a per unit mass basis, I mean, we've already talked about how we can have properties on a per unit mass basis. We could also have heat transfer on a per unit mass basis. So if we divide Q by M, then this is lowercase letter q. Okay? And we don't call it specific heat. We use the word specific when we're talking about properties per unit mass, but heat is not a property, it's just an energy transfer at the boundary, so we do not use the word specific heat. In fact, we use the word specific heat for something totally different. This we just call heat per unit mass. So lowercase letter q is the total heat divided by the mass, so this is going to be either kilojoules per kilogram in its units, or just BTUs per pound mass. Okay, so that's the heat per unit mass. We can also have rates of heat transfer. So if we were to take our heat and divide it by time, maybe I'll just write out the word time, then here we would write this as Q dot. Okay, we've seen the dot notation perhaps in our math, our calculus class. The dot just is the rate of something, the time rate of something. So Q dot will actually more formally be written as delta Q dt, and this is just the heat transfer rate. So the units are going to be kilojoules per second, or typically BTUs per second, although sometimes we'll have per minute or per hour, but typically we're just going to use per second as the time units here. So we have to be really careful when we're solving problems. Are we looking at a total amount of heat transfer? Are we looking at a rate of heat transfer? Are we looking about the heat that's transferred per unit mass of material? And we've got different notation for each of those possibilities. Another thing we have to realize is that if we undergo a process, and let's say this is a process from 1 to 2, whatever 1 and 2 represent, then what we do is we write subscripts. So if we see Q with the subscript 1, 2, then that tells me that we've just undergone a process from state point 1 to state point 2. The subscript 1, 2 is just to remind us of the nature of that process. Okay. Similarly, we could have lowercase q 1, 2. We could have q dot 1, 2. It really just depends upon the nature of the problem as to whether we use a capital or a lowercase or a dot. But we certainly want to put subscripts on whatever problem is at hand, just to make sure that we know what process is that we're dealing with. Okay. So these are just some basics for work. I'm sorry, for heat transfer. Now we're going to do exactly the same thing for work and look at its sign convention and its appropriate units and all of that. So in the same way that heat is not a property, work is not a property. Okay? Work, again, is an energy transfer at the boundary. Okay? It is not a property. All right, so we never want to assume it's a property. The units are going to be essentially the same as they were with regards to heat units, right? I mean, why shouldn't they? They're energy transfer, so the work is going to be, well, either kilojoules, okay, or now here things are a little bit different. If we consider work is actually you know, a force acting through some distance, as you may have learned in your dynamics class, well, then the units are going to be, well, again, I referred to this previously, force times distance would be pounds force times feet. So the pounds foot is sometimes the unit which is used for work. Now again, we could make a conversion into BTUs if we're solving one problem and that problem contains both heat transfer and work, then we can't use pounds foot and BTUs in one problem statement. You know, we are going to have to do some sort of a conversion, but these are nonetheless the typical units associated with work. One thing that's always nice to do as we begin talking about work is just refer back to the basic definition of work as, again, you would see in a dynamics class. Work, first of all, I'm just going to give it W. W be the word or the variable that we can use for work. And work is actually an integral of force dotted with a position change as we move through some process from some initial point 1 to some final point 2, right? So I just use underlines like that. That's the way I write vectors. Some instructors in like statics dynamics will put a line above it. Some will put like an arrow above it. I've always just put a little line below it. But basically that is our definition of work as we would have learned in a mechanics class. So let's just say that this is from mechanics. And as we're just talking about the units, well, you can see that those would be the right units, right? The units of force are going to be pounds force. The units of position are feet. So pounds foot are the appropriate units for work. Now you might wonder, well, what about kilojoules? That doesn't exactly look like force times distance. But again, we talked about that, right? A kilonewton is force. A meter is length. So a kilonewton meter is a kilojoule. They're the same. So the kilojoules would be the appropriate units in the SI unit, or we could write as kilonewton meter, but it's all essentially the same thing. Okay. So let's just continue. Again, like we saw for heat transfer, we can divide by mass. So if we look at the work and we divide it by the mass, then now this is going to be a lowercase w. So again, I have to make some distinction between my capital and my lowercase w's. So my lowercase w's are actually going to look more like the Greek letter omega. They'll have a rounded bottom like that. But that's not an omega. That's actually work per unit mass. So this is work per unit mass. Okay. Oh, by the way, it looks like I forgot my sign convention. So just to keep this in the same order, I should have talked about sign convention next. You'll notice here that if the force is in the same direction as the change in position, then both of those terms would be positive, so that the work numerically would be positive. So if we are actually, let's say we are the system, or I'm the system, and I'm pushing into the surroundings, then that means work being done to the surroundings by the system is considered positive work. And that's actually opposite of heat transfer, right? With heat transfer, heat added to the system was considered to be positive. Here, work being done by the system to the surroundings is considered positive. And that's entirely based upon the mechanical definition of work. So probably up in here, I should have mentioned this to begin with. That work is positive if it is done by the system onto the surroundings. Okay. So it's the opposite sign convention as for heat transfer. Opposite of that for heat transfer. So again, just something to be aware of. Now again, like heat transfer, we can have work per unit mass, as I mentioned just previously above. We could also have work per unit time. So if we have work over time, thank you. So if we have work over time, then we're going to write this as W dot. More formally, this should really be delta W dt. So some incremental amount of work done over some incremental amount of time, that's the work per unit time. And this would be, well, we wouldn't call it the work rate. We have a special name for it. It's called power. So the time rate of doing work is the same thing as power. All right, so that's our power. And again, we need to have the appropriate units. So the units are going to be either kilojoules per second. Well, it turns out that a kilojoule per second is defined as a kilowatt. So they're exactly the same. A kilojoule per second or a kilowatt mean exactly the same thing, and that's what we're going to use in the SI system, typically kilowatts. In the British system, then it's just going to be BTUs per second or horsepower. Now, 1 horsepower is not equal to a BTU per second, all right? They have absolutely nothing to do with one another. I can't tell you the exact numbers. It's something like 1 horsepower is about like 0.71 or thereabouts BTUs per second. But you'll have to look up the conversion factors. So, if you're solving a problem and, you're using kind of traditional British system units, you're going to somehow have to convert from horsepower into BTUs per second, or maybe into BTUs per hour, or maybe even into foot-pounds force per second or foot-pounds force per hour, just to get all the units to work out properly. So just be aware that unlike a kilojoule per second, which is exactly the same as a kilowatt, a BTU per second does not equal a horsepower. And again, use conversion factors. Make sure you use them appropriately, or else your numbers are just all going to come out wrong for any problem that you work on. Okay. Now, again, just like heat transfer, if we have a process from some, let's say, state point 1 to 2, then we would just use W12 as a subscript. If we have work per unit mass that we're analyzing, maybe we'll have lowercase w with the subscript 1, 2. If we're trying to figure out the power, then maybe we'd have just w dot 1, 2. So we need to make sure that we, again, use the appropriate subscript. By the way, you're not always going to have a 1 and a 2. I might have a problem where I go from 1 to 2 to 3 to 4 to 5. Maybe you'll have Q1, 2, and then Q2, 3, and Q3, 4, and Q4, 5. Or maybe work 1, 2, work 2, 3, et cetera, et cetera. Maybe I'll give you a problem where you start at point A and end at point B, right? Well, then you'll use the subscripts A and B instead of 1s and 2s. The point is, use whatever subscripts are applicable to the problem at hand. I'm not just going to make up numbers here. Typically, it's going to be 1 and a 2, but it may not always be. So, yeah, don't worry so much about that. Just be aware that we may have different sets of subscripts. Okay. Now, another thing that I want to point out, you may have noticed previously that when I wrote the time derivatives, for instance, I wrote q dot is delta q dt. I wrote w dot is delta w dt. Why did I write them that way? Why did I use the deltas instead of the d's? Okay, and for that matter, why did I write it q with the subscript 1, 2, or w with the subscript 1, 2? Why didn't I write, let's say, q2 minus q1 or w2 minus w1, something like that, kind of implying, the work from state 1 compared to the work at state 2, or the heat transfer state 1 compared to the heat transfer state 2. Well, there's actually specific reasons for that. From a thermodynamic point of view, we would understand that only thermodynamic properties are point functions, meaning that they're differentiable. They do not depend upon the path of the process taken. They only depend upon the thermodynamic state. On the other hand, work and heat transfer are not properties, are they? They're absolutely not properties. They're energy transfers at the boundary. They depend upon how we get from state point 1 to state point 2. I mean, if I just take, I don't know, how about this iPad here? You might think it would take the same amount of work to get this iPad from here over to there. It's just some force moving through some distance. But that's not really true. I can start here. This is my initial property, my initial state. And I could actually move this thing in a big arc and end up at the same state point too. But it took me a lot more force over a much larger distance. The work clearly depends upon the path I take, right? I have the same thermodynamic state. I start at point 1, I end at point 2, but I have 2 possible different paths. So it should be pretty clear, just based on this one example, that work is a path function. It depends upon the path that we take, and as such, I can't write it as an exact differential. I can't write dw dt. That would imply that there's some work somehow inherent to the system, or that it's somehow a property. It's not. And the same thing with the heat transfer. I can't write dq dt. There's no inherent heat transfer at any one particular state. The heat transfer occurs depending upon the path that I take as I get from some initial point 1 to some final point 2. So properties are considered point functions. Heat transfer and work are considered path functions. If you have a point function, then it's differentiable, and I could use just d's. I could, if I had to, I can use d's for the differential. Q and W are path functions. They depend upon the path. So, you know, the point is you can't use Q12. You can't use W12. There's no such thing. I'm sorry, I said that wrong. You can't use Q2 minus Q1 to represent the change in heat transfer from 1 to 2. You can't write W2 minus 1. W1. You can only write Q with the subscripts or W with the subscripts, implying that there's a certain amount of heat transfer, a certain amount of work that occurs. Anyway, it looks like that's all the time that I have for today. Oh, got to move it up. Yep, thank you. Let me again note that there are different forms of, or modes, if you will, of heat transfer. There's different modes of work that we're not going to cover in this class. In Chapter 2, I think it's Section 2.4 and 2.5, it does talk about some of these different modes of work, like mixing, like stretching of a wire, like rotation on a shaft. It's not like we aren't going to talk about those things, but we're not going to have any equations to solve them. If we use any of those, I will make sure I give them to you in lecture so you're aware of them. But in general, I'm going to just skip Sections 2.4 and 2.5. I think those are the right sections. It's the sections that deal with the other forms of work. I should really look on my book to make sure, but I didn't bring my book today. So anyway, that's all for today. Remember that Wednesday your first homework set is due, so don't forget to bring that with you. And any last questions about anything today? One-sided. Yeah, I'd appreciate it if it's one-sided. Oh yeah, the last thing, is there anybody who's still trying to add this class? I still have a problem that the class is full. Are you guys in the corners comfortable? Can you see both the screens if you had to? I'll just go ahead and add you last 2 students. Just why not? Be a nice guy for a change, right? So just to make sure you are the same 2 who are coming every day, that's Thon Nguyen and Ulysses Sanchez, correct?